So now we have come to translation from SSA form. And the basic idea is to take one phi function at a time and make copy statements in the predecessors. So in this vertex, we set A3 to A1 and B6 to B4. And in this vertex, we set A3 to A2 and B6 to B5. And then we can delete the phi functions. This means that there must be a vertex that we can put these copy statements to. So we put them here, but if this vertex would not exist, what would we do then? Suppose the program would look like this, and this does not exist. Then we don't want this, but if it was like that, then we would perhaps insert A3 set to A1 here, but that's wrong. We might want to set it before the conditional branch so that it's certainly executed, but we don't want to execute it if we go in this direction. This edge, red edge here, it's called a critical edge. And the critical edge is from a vertex with multiple successors to a vertex with multiple predecessors. And we don't want critical edges, so we remove them by inserting empty vertices. And we do that actually before dominance analysis. Okay, so the code will look like this. Okay, so when we create these copy statements in the predecessors, we have to make a little check. Otherwise, we can get the wrong output. So if we do A2 set to A1 and B2 set to B1, that's fine. But the right operand, these operands, they will create problems. The semantics of a phi function, or actually of all the phi functions taken together, is that we read the operands, we read all operands in one atomic operation, and then we set the destination, the left-hand side, to the corresponding value of the operand. Therefore, the order of the phi functions doesn't matter. We can put them in any order. It's actually a set of phi functions. But we should, when we translate back, we need to check that there is no dependence, that we use a variable that we have, we can see here. Here we assign A2, and then we use A2. So the atomic read of all the operands is lost, since we execute these assignments, these copy statements sequentially. Okay, so what's wrong here? Well, what I just said. What we need to do is to save the value of a variable that will be needed in the future. I mean the old value. So here we should use the old value and not that value. Okay, so we save it, and then we can use it when we needed the previous value of A2. Okay, so we can also detect the use of uninitialized variable and complain. That's a good idea to do in the compiler. When you have done this translation to SSA form and run in the VCC compiler, you will notice that the program typically becomes slower. And the reason for that is the many copy statements. As this is to be expected, because we have not done any optimization yet. But what you will do as the very first optimization on SSA form in the second lab is to optimize copy statement like this. And this is during translation to SSA form. What we can do is to remove this copy statement, and instead of doing normal renaming, I mean, what we would do is to say something, for instance, like this: A3 equals, set to B5 or something like that. But what we can do instead, okay, so suppose we have these renamed stacks, B, and here B5 is on the top of the stack, okay, and here we may have, for instance, A2. And what we can do, instead of pushing A3 and using the top of the stack of B, that means B5, we can instead push B5 on the stack of A and then remove this. Okay, so it's very simple.